So this is our first video for guided notes for Math 1332 Contemporary Math. We're going to start the first section on inductive and deductive reasoning. But before we start talking about the two types of reasoning, we're going to address number concepts and how we classify numbers. Now we're going to talk about all possibilities, but we're not going to use all possibilities in this course. For this course, we're going to focus primarily on counting numbers or natural numbers. But we want to address the fact that when we deal with number systems, we have two main classifications. Numbers are either real or they're imaginary. And they can't be both. You either have a real number or an imaginary number. Now, imaginary numbers aren't made up. When they were first thought of, they were theoretical. They were a way for mathematicians to continue their research in the way the numbers were leading. But since then, they have become very, very useful in areas specifically dealing with electricity, so for electrical engineers, and also with what we call signal processing. And signal processing is what wireless and cellular networks use. Now, I don't know the details of those things, but these are major areas of study and of practical application where imaginary numbers are put to use. Now, when we get to math, a lot of the time we get really anxious and we forget the things that we already know. You know what these words mean in English. You know real and imaginary. That's what they mean in math, in that they cannot be both, a number cannot be both real and imaginary. Now, an imaginary number is sometimes called a complex number. A complex number because it has two parts. It has a real part and an imaginary part. This is the general term for a complex imaginary number, a plus bi, where a is the real part and bi is the imaginary part. So for example, 2 plus 5i is a complex imaginary number because you have a real part and an imaginary part. Negative 3 minus 7i is another example of an complex imaginary number. And then we have 10i and negative 21i. For these two imaginary numbers, the real part would be 0, so we don't write it down. Now, if the imaginary part were 0, so this bi goes away, then we do have a real number. Because it is a purely real number, that imaginary part does not exist. Okay. Real numbers are broken down into two major areas, rational and irrational. That prefix ir means not. So if a number is irrational, that means it is not rational. So just like our number can't be both real and imaginary at the same time, it cannot be both rational and irrational at the same time. Let's talk about these irrational numbers first. An irrational number cannot be written as a fraction. Now, when we talk about a fraction, we're talking about something in the form a over b, a divided by b, where a is my numerator, numerator, and b is my denominator, denominator. If you have trouble remembering which piece is which, the denominator is down. Denominator and down both start with D. So a fraction can be written with 2 over 3 or negative 7 over 12. If a number can be written as a fraction, it's rational. If it cannot be written as a fraction, it's irrational. If it can't be written as a fraction, that means that if I put it in decimal form, the decimal would, the decimal that is going to never end or repeats. A decimal that never ends or repeats. An irrational number has a decimal that never ends or repeats. Examples of an irrational number. I've got pi. You're probably familiar with that irrational symbol pi. We usually simplify it as 3.14. But if you pull out your calculator and you find that pi button on your calculator, when I press pi and hit enter, I see that my decimal goes all the way across the screen and then I run out of room. And the decimal doesn't end, it just stops because I ran out of space on my calculator. Pi has a never-ending, never-repeating decimal. The other example I have here is square root 2. If I do square root 2 in my calculator, square root is the second function above the x squared button. So you see x squared right here, square root is right above it. So I'm going to push second function x squared, and that pulls up my square root symbol. And if I do square root 2 and hit enter, you see again I have a decimal that never ends and never repeats. So these are examples of irrational numbers. Now we're going to stop just a second and talk about what a square root means. Just in case you've forgotten about that and you're wondering why it matters, because not every square root is irrational. The square root is the inverse operation of squaring something. Just like addition and subtraction undo each other. If I do 2 plus 3, I get 5. If I go backwards, I could say 5 minus 3 is 2. Addition and subtraction are inverse operations. Multiplication and division are also inverse operations. 2 times 3 is 6, and 6 divided by 3 is 2. They undo each other. The inverse operation of the square root is to square something. If I start with my integers and I square them, let's just write down some numbers to square. So I've got 1 squared through 6 squared. 1 squared just means to multiply 1 times itself 2 times. So this would be 1 times 1, which is just 1. 2 squared would be 2 times 2, which is 4. 3 squared would be 3 times 3, which is 9. And if I continue that process, 4 squared would be 16. 5 squared would be 25. And 6 squared would be 36. So these numbers are my perfect square numbers. If I undo that act of squaring by taking the square root of these perfect squares, for example, if I ask for the square root of 1, I'm saying what number times itself gives me 1? Well, that's 1. Square root 4, what number times itself gives me 4? Well, 2. Square root 9, what number times itself gives me 9? That would be 3. If I skip on down, what about the square root of 100? What number times itself gives me 100? Well, that is 10. 10 times 10, or 10 squared, is 100, so the square root of 100 is 10. What if I don't start with a perfect square number, though? What if I ask you for the square root of 5? Well, what number times itself gives me 5? I know that the square root of 4 is 2, and 4 is just less than 5. And I know the square root of 9 is 3, and 9 is more than 5. So that means that the square root of 5 has to be somewhere between 2 and 3. Let's do it with our calculator. Remember, I'm going to do second function of that x squared button to get my square root. Square root 5 is, look at that, 2.2 approximately. We have to round it off because it's irrational. It's not rational because 5 is not a perfect square. Okay, so those are our irrational real numbers. Now let's talk about our rational real numbers. An irrational real number cannot be written as a fraction. A rational real number can be written as a fraction. So here's some examples I gave you. 5 over 1 is just 5. 1 over 3, 1/3, is equal to 0.3 repeating. That's what that line over the 3 means. Now, when I have a fraction, if I want to turn it into a decimal, I just treat that fraction bar as a division sign. So when I want to turn 1/3 into a decimal, I just type in 1 divided by 3. There's my fraction, 1/3. Hit enter, and you see you get that repeating decimal. So 1/3 is equal to 0.3 repeating. 1/4 as a fraction is equal to 0.25. That's a terminating decimal. It ends. Okay, so those are rational numbers that can be written as a fraction. Now, what if it isn't something that would turn into a decimal other than 0? Well, if it could be written as a fraction, but simplifies to a decimal of something 0.0, then it is either an integer, or more specifically a whole number, or more specifically, a natural number. Now, integers are what we call our positive and negative whole numbers. Let's just do that. Positive and negative whole numbers. And then the whole numbers are just the positive ones. So my set of integers would be, for example, -3, -2, 1, -1, 0, 1, 2, 3, etc. in both directions. So infinitely to the negative direction, infinitely to the positive direction. My positive whole numbers, my negatives, and 0 is my set of integers. Integers are rational because they could be written as fractions. -3/1, -2/1, -1/1. Then, if I want to be more specific, like we just said, we talk about our whole numbers. The whole numbers are 0 to the positive direction. So 0, 1, 2, 3, 4, etc. On and on forever in a positive direction. So integers includes negatives, 0, and positives, everything with a denominator of 1. Whole numbers include 0 and the positives, all with a denominator of 1. And then my smallest set are my counting or natural numbers. They do not include 0. It's just 1, 2, 3, etc. And I write that little ... ellipsis to show it goes on forever. Now this is my most specific, my smallest set, and these are the numbers that we're going to focus on to start with while we talk about set theory. Counting or natural numbers. When you're little, when you have a baby and they're learning to count, they learn to count things. Well, they have to have something to count. They don't have a concept of 0. They start with 1. 1, 2, 3. They're counting cookies, they're counting napkins, they're counting stuffed animals, they're counting people in the room, but you start with 1. Those are our counting numbers or our natural numbers. After you master that art of counting, then you start to develop a concept of nothingness or of 0. And that's when we talk about whole numbers. There are counting numbers and 0. After that comes a concept and an understanding of negative numbers. We usually start that with numbers or with with money or temperatures, where we have a concrete application of negatives. Our integers are our positives, our 0, and our negative whole numbers, basically. And then all of our rational numbers include all of these things, as well as things that would have a decimal that's not 0. So this 1/3, 1/4, things like that. All right, these are all rational. If a number is real, it's either rational or irrational. If a number is not real, it's imaginary. And we don't break imaginary down into any other simpler sets. It's just imaginary. So those are how all of our number concepts fit together. Again, we're not going to be working with all of these this semester. It's just a good idea to know where you stand and know what numbers mean. We're going to focus on starting with inductive and deductive reasoning. Now, inductive reasoning is when I arrive at a general conclusion from specific examples. Inductive reasoning is to arrive at a general conclusion from specific examples or observations. So with inductive reasoning, I'm starting with specifics and I'm moving toward general. With inductive reasoning, I'm starting specific and I'm moving toward general. For example, inductive reasoning. I start looking through the list of teachers at an elementary school, and I see that the first 10 teachers listed are all women. Well, I may make a general conclusion based on those specific examples that all of the teachers at that elementary school are women. That may be right, it may be wrong. but that's how inductive reasoning works. Now let's do a mathematical example of inductive reasoning. Will the sum of an odd and an even number be odd or even? Well, first let's talk about what these terms mean, odd versus even. Usually we start by thinking about what an even number is. An even number is divisible by 2. An odd number is not divisible by 2. So if I add together an odd number to an even number, will the sum of that, and the sum is the answer to an addition problem, will the sum of that be odd or even? Well, you might come to a hypothesis. You guess what you think it will be, make a prediction. But if we want to have an informed prediction, we need to think of some examples so that we kind of have something to build our case on. So let's add some odd and even numbers together. An odd number is 5. 5 is an odd number. And like I said, an even number is divisible by 2. So 2 is an example of an even number. If I add 5 plus 2, I get 7. Well, 3 is an odd number and 10 is an even number. 3 plus 10 is 13, and I'm just coming up with values. It doesn't matter what numbers you use as long as you follow the requirements of odd and even. 9 is an odd number, and 6 is an even number, and 9 plus 6 is 15. So these are the 3 sums I have gotten out of those 3 examples. So based on these 3 examples, I'm going to predict that anytime I add an odd number to an even number, I predict that the sum will be odd because these 3 sums are odd. Now, the thing about inductive reasoning is that inductive reasoning is impossible to prove. Inductive reasoning is impossible to prove. Now, it's impossible to prove because it only takes one counterexample to show that it's false. It only takes one counterexample to show the conclusion is false. So these are 3 examples that show that my conclusion would be that the sum will be odd. But if I can come up with one example that counters that is a counterexample where I add an odd plus an even number and I get an even sum, then that would prove it false. I can't prove it true because to prove it true, I would have to check every possible sum of every possible odd plus even number. And there are literally an infinite number of options. I cannot check them all. Since I can't check every possibility and it would only take one false to disprove my conclusion, that means that inductive reasoning is impossible to prove. Inductive is impossible to prove. Okay, let's look at our next page of notes. We're going to work through an example. Now, I'm going to do one. You need to do a different one at home, okay? So when we're doing this in class, we're in groups, and so each table has 4 examples because there's a group of 4 plus mine, so they have 5 different examples. We don't have that luxury. We're going to do my example and your example. You might could do a couple, but the start says to pick a number, any number. I'm picking 11. You do not pick 11. Pick something else. Now we're going to do each of these 4 steps to our number. So I'm going to be working with 11. You're going to be working with your number. The first thing you're supposed to do is multiply your number by 4. So for me, I take 11 times 4 and I get 44. You know what? I'm going to set up a second example over here, just so you have 2 to look at. I'm going to use 11 and I'm going to use 6. Well, if I multiplied 6 times 4, I would get 24. And if you can't do this in your head, feel free to pull out your calculator and do it with that. All right, next I'm going to take this product. A product is an answer to a multiplication problem. I'm going to take my product and I'm going to add 2 to that product. Well, 44 plus 2 is 46. If I'm doing my second example, 24 plus 2 would be 26. And you're doing your example. Now, when I add something, I get a sum. I'm going to take that sum and divide it by 2. Well, 46 divided by 2 is 23, and 26 divided by 2 is 13. Your number that you started with over here, you will be working through another set of answers. When I divide something, I get a quotient. I'm going to take that quotient and subtract 1 from it. Well, if I subtract 1 from 23, I get 22. If I subtract 1 from 13, I get 12. Notice that for my first example, I started with 11 and I ended up with 22. For my second example, I started with 6 and I ended up with 12. Compare what you started with to what you ended up, and we're going to form a generalization. It looks like, based on the examples we've done, that if I follow this set of steps, I am doubling the original number. I am doubling the original number. Now, this is the same thing as multiplying by 2. So that I could predict for you what number you would end up with. Or you could tell me your final number and I could tell you what you started with. It's kind of a magic trick, math magic. This is inductive reasoning. And it is an example of inductive reasoning because we are starting with specific examples and we are forming general conclusions from those specific examples. Now we're going to move on and talk about deductive reasoning. With deductive reasoning, I go back the other direction. I start with a general statement and I reason it down to a specific conclusion. Deductive reasoning starts with a general statement and reasons to a specific conclusion. Now, we use this when we want to prove something. We want to prove that our conjecture or our hypothesis is true or false. I have to use deductive reasoning because remember we said that you cannot prove inductive reasoning. It would just take one counterexample to show it false. So you can't do every counterexample typically, so you can't prove it. With deductive reasoning, however, I start with something that's completely general, and because of that, I can prove my conjecture. I can prove my generalization and say, yes, this is absolutely always true, or yes, this is absolutely always false. Okay, we're going to prove that that procedure above would always result in twice the original number. Now, the way we're going to do is we're going to say, when we say pick a number, any number, we're going to pick a variable and we're going to use n to represent any number. N for number. That variable n represents any number, just like it does in algebra. Now we're going to represent our steps with algebraic expressions. So if I take n, my any number, and I multiply it by 4, that looks like 4n. Now, because we're using a variable, we can all be doing the same thing. Your variable could be a or b or c or d, but we can all just use n because n or a or b or whatever variable you pick represents literally anything, any number I want to use. So if I multiply my variable, my n, times 4, I have 4n. Then it says to add 2. Okay, so I take 4n and I add 2. Then it says to divide that by 2. So let's go over to the side and let's take our 4n plus 2 and divide it by 2. Now, these are two separate terms. They're not alike because this first term includes a variable, the second term does not. So the easiest way to do the division and simplify is going to be to break it apart so that I have 4n over 2 plus 2 over 2. You see how I took my two terms in the numerator and I split them, and I kept the denominator under both of those terms. Well, 4n divided by 2 is 2n. And 2 divided by 2 is 1. So 4n over 2 is 2n, plus 2 over 2 is 1. That is the quotient. Now I'm going to take that quotient and I'm going to subtract 1 from it. That's my last step. If I take 2n plus 1 and I subtract that 1, those like terms, plus 1 minus 1, those are opposites. They add to 0. I'm left with just 2n. Then if I compare what I started with to what I ended with, I see that yes, in general, no matter what number I were to choose, I would end up with twice what I started with. So I proved my generalization. All right, let's look at the next page. Keep in mind that the benefit of a video is that you can pause and come back. If you get overwhelmed, you need to take a break, just do that. Okay, we are going to use inductive reasoning to find the next few numbers for each of these 5 examples. Inductive reasoning means we're starting with specifics, specific examples, and forming general patterns based on that. So, for example, for this first one, I'm given 19, 24, 29, 34, 39, and I'm asked for the next 2 numbers. Well, as I look at these numbers and compare how I'm getting from one to the next, I figure out that I'm adding 5 each time. So if I add 5 here, I get 44, and then if I add 5 again, I get 49, and I could keep going. So my pattern is that I add 5 to the previous number. That's my pattern. That's my generalization. I want you to look at these next 4, and they're not all simply adding a number, adding a value. So look at the next 4, predict the 2 that follow, the 2 terms that would follow, and see what you think the pattern looks like. I'm going to pause the video and do mine, so you pause your video and do yours, and then come back. Okay, so I filled in my next 2 numbers for each of those. To get the next 2 numbers for that second one, I used multiplication by 4. I multiplied each term by 4 to get the next term. For that third pattern, it's going up and then down, up and then down, and every time I go down, I go back to 1. There's different ways you could write this pattern. When we're in class, we talk about at least 2 or 3 different ways to say what the pattern would be. My favorite that students have given to me so far is that we add and then subtract multiples of 3. Add, then subtract multiples of 3. So for example, 3 times 1 is 3. So 1 plus 3 is 4, minus 3 is 1. My next multiple of 3 would be 6. 1 plus 6 is 7, minus 6 is 1. My next multiple of 3 is 9. 1 plus 9 minus 9. My next multiple of 3 would be 12, etc., etc. The fourth pattern, I see that my numerator does not change. 1 is the same thing as 1 over 1. So my numerator does not change all the way across. I'm just adding 1 in the denominator. So it is not increasing or decreasing by a specific amount. The denominator is just increasing by 1 each time. And my final pattern is to add 1 more each time. Add 1 more each time. So the first time I added 3, and then I added 4, and then I added 5, add 6, add 7, add 8, and I would add 9 if I kept on going. Okay. Our next section says to prove false by using inductive reasoning. Remember that inductive reasoning is proven false by a single counterexample. So I am looking for one example that says, no, that's not right. No singers appear in movies. Well, that is false. And my counterexample for that is Elvis. I'm an Elvis Presley fan, and he made a ton of movies. There are lots and lots of examples of singers that appear in movies. The second one, if a number is multiplied by itself, the result is even. Well, that is also false. 3 times 3 is 9, and 9 is odd. What's another one? What about 5 times 5? Well, 5 times 5 is 25, and 25 is odd. So these are both false conclusions, and we used inductive reasoning to show that they were false because we found a single counterexample. All right, let's look at the next one. All four-sided figures have right angles. Well, that's not true. I can draw any four-sided figure other than a square or a rectangle. There's a trapezoid right there. Parallelogram is a four-sided figure that does not have right angles. Just a weird four-sided figure where all the sides are different lengths would not have right angles. My last example, if a number is odd, then it ends in 5. Well, 9 is odd and it doesn't end in 5. 3 is odd and it doesn't end in 5. 2,147 is odd and it doesn't end in 5. So all 4 of these are shown false using inductive reasoning because we found a single counterexample. So those were uses of inductive reasoning. Now we are going to use deductive reasoning. When we use deductive reasoning, we start with general statements and we form a conclusion, a specific conclusion from those general statements. Now, my general statements that I am giving you, I'm not asking you to judge them. You don't have to determine if they are true or false. These are your general statements that you're given. You assume that they are true, and you draw a valid conclusion based on those general statements. All dogs bark. My dog's name is Hank. Based on those 2 statements, what can you conclude? Well, you can conclude that Hank barks. That is my specific conclusion formed from these 2 general statements. Now, this conclusion may be is a valid conclusion. We're not judging whether it's true or false. It's valid because it follows directly from my 2 statements. All right, the next one. All math classes are enlightening. This is a math class. I can form the specific conclusion that this class is enlightening. All right, there's my specific conclusion drawn from these 2 general statements. This is a valid conclusion. I want you to do the next 3. I'm going to pause the video. You pause your video, do your 3, and then compare. All right, I think I said 3. There were actually 4 more conclusions. For this next one, I was given 3 statements, 3 general statements. All students do laundry on Saturday. Joe is a student. Today is Saturday. The valid conclusion that I can draw from that is that Joe is doing laundry. Now, I don't want to restate things that are given to me directly in my generalizations. I want to use them to form a conclusion. The next one, every time you took a test, you got stressed out. You get stressed out. You took a test on Monday, therefore you were stressed on Monday. All Martians are green. Marie is a Martian. Therefore, Marie is green. Again, we're not judging true or false, realistic or made up. We are just forming a valid conclusion based on what we're told. No students like pop quizzes. Miguel likes pop quizzes. Therefore, Miguel must not be a student. Okay. Was inductive or deductive reasoning used? Now that question applies to these 3 statements. If I say, Mike, Dan, Marie, and Ange smoked and got lung cancer, therefore, everyone who smokes gets lung cancer. I started with 1, 2, 3, 4 examples, and I formed a general conclusion. When I go from examples to generalization, that is inductive reasoning. specific examples to general conclusion is inductive reasoning. On the next one, it says, I know that x is greater than y, and I know that y is greater than z, therefore x is greater than z. Well, these are variables. These are not specific examples. These are general cases. X can represent any number. So if this is a true relationship and this is a true relationship, then this relationship is also true. Well, that is an example of deductive reasoning because I'm using generalizations. And then on this last one, I'm given that 3 is prime, 5 is prime, and 7 is prime. Therefore, all odds are prime. So again, 3 examples, and then I give a general conclusion about everything. That is inductive reasoning when I go from specific to general. By the way, is this generalization, is this conclusion true? Can you think of a counterexample? Can you think of an odd number that is not prime? Remember, first of all, that the definition for a prime number is that the only way to multiply and get that number is 1 times itself. For example, 3 is prime because my only factors of 3 are 3 times 1. 5 is prime because the only way I can get there is 5 times 1. 7 is prime because 7 times 1. All odds are prime is actually a false conclusion. My counterexample that I'm going to choose to give is 9. 9 is not prime. 9 is either 3 times 3 or 9 times 1, so it is not prime. You might have said 27. 27 could be 3 times 9, or it could be 1 times 27, so it's not prime. But I only need one counterexample. I wouldn't need to find more than one counterexample to prove that is to disprove that conclusion. All right, let's kind of review what we've talked about with inductive and deductive reasoning. You can look back at your notes and think about which one it is referencing, inductive or deductive. When I'm using patterns, patterns are specific examples. So inductive reasoning uses patterns. Which kind of reasoning uses general statements to help me draw specific conclusions? General to specific is deductive. What kind of reasoning can only be proved false? I can't prove it true. Well, inductive, because it just takes that one counterexample. What kind of reasoning looks at specific examples and then draws general conclusions? So it goes specific to general. That one is inductive. What kind of reasoning can be proven as true or false? That one is deductive. And then it says to use deductive reasoning to solve this logic puzzle. And then use the example below to predict the 4th line. I want you to pause the video, work through 6 and 7, and then come back to me. Okay, so let's talk about number 6 a little bit. Hopefully you got it right. If you didn't, I want to direct you to the second statement. Smith married Brown's sister. So Brown cannot be an only child. And the teller is an only child, so Brown can't be the teller. Smith earns more than the manager, and the teller earns the least. So since Smith earns more than the manager, Smith can't be the teller, and Smith can't be the manager, which means Smith has to be the cashier. And then you can narrow the rest of it down from there. For number 7, what kind of reasoning are we using? Well, we've got 4 examples and we fill out the 5th one. When we start with examples, we are doing inductive reasoning. Hopefully you found the pattern. This first value, I have 1, 2, 1, 3, 2, 1, 4, 3, 2, 1. So this next row is going to start with 5, always a 9, always -1. And each time here, I am adding an 8. And I'm counting up. So 0, 1, 2, 3, 4. Okay, let's look at our next page. Look at these two arguments. Which inductive argument do you think is stronger? Well, the first argument is much stronger than the second. Why is that first argument stronger? It's stronger because I have more specific examples, more cases. For my first argument, I have 380,000 freshmen at 722 different universities, and I sampled that many, so I have that many examples. On the second argument, I have 3 examples: kindergarten, first grade, and second grade teachers. So I have many, many more examples on the first argument. That makes it a much stronger argument. Now we're going to do some more number tricks, just a couple more to talk about the difference between inductive and deductive reasoning. Again, just like the last one, I'm going to pick a number. You don't pick my number, pick a different number. I encourage you once more to pause the video, work through this number trick, and come up with your generalization, and then come back and look at my example. I'm going to pick 4 as my number, so you pick something else. Do not pick 4. Okay, I went ahead and did an extra example. If you got lucky, then you chose 7 as well, and I'm checking your math for you. But when I started with 4, I ended up with 8. When I started with 7, I ended up with 14. You probably have a different example that you worked out. Hopefully, your example showed that when we do these steps, it doubles our original number. One more number trick. We're going to first devise a shortcut or a generalization to help you find the final result based just on the original number. And then we're going to come in and we're going to do a general case to prove whether or not we were right or wrong, to prove whether our generalization was true or false. So let's do our examples again. I'm going to pick, for this one, I'm going to pick 15. So we're going to do inductive by picking a specific example, and the number I'm going to select is 15. You select something else. We're going to take the number we're starting with, subtract 2, take that result and multiply it by 6. Again, feel free to use your calculator if you need to. Take that product and add 2 to it. Take that sum and divide it by 2. Add 5 to that quotient, and then compare what you started with to what you finished with. What's your generalization here? Well, my generalization is that if I do this, it is going to triple my original number. So for example, if my starting number is 10, I would end up with 30. If my starting number were 5, I would end up with 15. If my starting number were 11, I would end up with 33. If I'm right, and my generalization is that I'm going to triple my original value. Let's check our generalization and see whether or not we're right. If we do deductive reasoning, instead of working with a specific example, we start with a variable. So I'm going to use n for any number. That's my generalization. Or my general number. I'm going to subtract 2 from that. So if I subtract 2 from n, I have n minus 2. Then it says to multiply that difference, that result, by 6. Well, if I multiply by 6, that's 6 times n minus 2, which means I need to distribute. 6 times n is 6n, and 6 times negative 2 is minus 12. After I multiply my result by 6, I want to add 2. So I'm going to take this, I'm going to say plus 2. My like terms would be the negative 12 plus 2, and negative 12 plus 2 is negative 10. So here I have 6n minus 10. The next step is to divide that result by 2. So I have 6n divided by 2 minus 10 divided by 2. Well, 6 divided by 2 is 3, so that first term is 3n. And 10 divided by 2 is 5, so I have 3n minus 5. And my last step is to add 5. So if I add 5 there, negative 5 and positive 5 are opposites. They add to 0, so I'm left with 3n. So in general, if I start with n, I finish with 3n, and I have tripled my result, so my generalization was true. We did a good job. Okay, last page. Consider that those last two problems that we just did. We did the inductive method and then the deductive method. When you found the generalization, which way were you reasoning? Well, when we start with specifics and find a generalization, we're using inductive reasoning. We go from specific examples to a general conclusion. That is inductive. Can I prove something using this reasoning? No, I can't. I cannot prove anything using inductive reasoning because I would only need one counterexample to disprove it, to show it's false. Can't check everything. Usually an infinite number of examples. Can't check them all, so I cannot prove something when I'm using inductive reasoning. When I went back to that problem, how did I go about proving my generalization true? Well, I used n. I started with a general term. When I did that, when I used that general term, what kind of reasoning were we doing? Then we were doing deductive reasoning. And when I'm using general to specific, when I go general to specific, I'm using deductive reasoning, and it can be proved true or false.